Hello, welcome to Cosmology Talks. Today we have Keir Rogers, who is a postdoc at the Dunlap Institute in Toronto. He's talking today about constraining ultralight axions with both CMB data and BOSS data simultaneously. This is a really interesting paper because Keir and collaborators have been extremely comprehensive at what they've looked at in terms of the axion masses that they're constraining and the allowed density as a fraction of the total density of the universe for each mass. Ultralight axions affect the CMB and the clustering of matter in BOSS differently, so the two datasets do complement each other quite well. And there is a hint of something a bit curious at one particular mass, where BOSS might even favor a non-zero energy density, although Planck doesn't. So very keen to hear. So I'm very keen to hear Keir's thoughts on what the physics is that might be going on there. So welcome, Keir. Do you want to start by telling us briefly about your paper?
Yes, thanks, Sean. There's kind of two overarching goals. So the first is, as you made very clear, that we want to put empirical constraints on ultralight axions as a well-motivated candidate to be the dark matter, but also they can contribute to be some of the dark energy as well, depending on the mass of the particle. And this has been looked at a lot with Planck CMB data going back over a decade, and in this work and in a precursor work, we wanted to add in galaxy clustering information, specifically from the BOSS survey, and also to start to look at what high-resolution CMB data, i.e. ACT and SBT, can say about axions, because they will probe, higher resolution essentially means smaller scales in the universe, and that's where the effects of axions tend to be strongest. And then the other aspect of this is the S8 tension. So we wanted to see, bearing in mind that axions suppress clustering relative to cold dark matter, they seem like a natural candidate to get lower values of S8, the amplitude of the clustering. So we wanted to investigate whether they were suitable for resolving this apparent mild tension we have at the moment.
Yeah, one of the things I quite like about the way you present the results, I mean, it's not unique to you, but it is not necessarily common, is instead of saying these are the masses that are ruled out at being 100% of the dark matter or 100% of the dark energy, like a bunch of constraints on the fraction, because it's quite possible that 10% of the dark matter is ultralight axions, and then, maybe they're suppressing the growth of structure just a little bit, but not as much as if they were 100%. So if people are remembering this talk in 6 months or a year, and there are only two things that they're able to remember, what would you want those two things to be?
So I think there is a sort of big picture story here, which is that, we've had a huge amount of success with the cosmic microwave background, establishing a standard model, and obviously it contains things that we don't understand, so we want to find a more complete cosmological model, and axions can be part of that, but in particular, we're going to BOSS is just the start of the huge amount of large-scale structure data that we're going to have. And so the ability to put, competitive constraints on new physics from large-scale structure alone even, especially in combination with CMB, I think is going to be very powerful. And hopefully this is part of that story. And also, I think that the results of our investigation to the question about S8 is that it could have something to do with the S8 tension, and so I hope that motivates people to think about that more as well.
Cool. And no link to the Hubble tension simultaneously, though, just
not by itself. Yes. So in fact, if you have, we'll talk about this in the talk later on, but if you have dark energy like axions, they actually exacerbate the Hubble tension slightly. But there are other axion-like particles, like the early dark energy proposals, that can address Hubble.
Cool. And I guess that's one of the things about axions is that in fundamental physics theories they tend to show up a lot. So it's not too surprising if there's more than one showing up in the history of the universe.
Yeah.
Cool. Well, let's get into the background now. Why is this an important thing to be looking at in 2022? I guess you're talking about the BOSS data. It's recently released, and I guess DESI's coming in the very near future, so this is relevant in that sense. And you've also briefly mentioned why ultralight axions might themselves be interesting, but please go into more details.
Again, there's a big picture motivation here, which is we have evidence for dark matter, which goes back, over a century, and particle physicists have been searching for the dark matter, assuming some new species of fundamental particle through different approaches, through high energy colliders to produce dark matter, through direct and indirect detection. But it could be that the dark matter has no other interaction with the standard model except through gravity. And so the only way that we may be able to learn anything about the dark matter is through its gravitational interaction. And so that means through astrophysical and cosmological observations. Now, of course, the fundamental challenge there is that it is not visible, and so we must use indirect traces of the dark matter, and so we have to be very careful about how we model the visible stuff, typically the gas, the intergalactic gas, and in this work we're now using the collapsed gas, the galaxies, to trace how the dark matter is behaving. But you can connect that to the fundamental nature of the dark matter. Once you accept that, then you can start to think about, well, what sorts of dark matter models can you constrain? And so here is a sort of very top-level schematic view of the dark matter model space, where I've ordered different classes of dark matter model by the mass of their fundamental particle. And so here you could go from the very heaviest fundamental particles with masses around the Planck mass, all the way down to the very lightest, which is this ultralight axion regime, atom below 10 to the minus 27 electron volts. And so historically, we've focused on the WIMP, these massive particles around a TeV, but because of the continuing non-detection of WIMPs at colliders and through direct and indirect detection, that motivates quite broadly in the dark matter community a kind of shift to consider other well-motivated alternatives to the WIMP. But then you need new detection strategies to look for these particles, as they won't show up in things like colliders necessarily.
You've singled out here canonical 10 to the minus 22 EV. Is there a fundamental physics reason why that's favoured, or is that literally just because it had the most interesting effects in galaxies?
Exactly. So really, and historically, and in fact, it's probably most well motivated from the astrophysical considerations. So the fact that it had just the right mass to create the right particle wavelength, that it could produce cores in the senses of dwarf galaxies. It would suppress the formation of satellite galaxies for the Milky Way. And so really for that coincidence of reasons, it attracted a lot of attention, this particular mass scale, to resolve these issues.
But from like fundamental physics, 10 to the minus 24 or 10 to the minus 18 would be just as likely.
There is some argument that you can motivate a kind of mass around 10 to the minus 22 EV, being all the dark matter, gives you a kind of early universe energy scale somewhere around the gut scale. And so there's a sort of coincidence that, you could associate the production of axions of that mass being at that energy density with that energy scale. And so that's there is some motivation in that as well. So some of the papers by Lam Hui talk about this. But I think from astrophysical point of view, to really assess these problems, you need much more sophisticated simulations of small scales that include astrophysical and baryonic effects. So we know that it is possible to produce cores using supernova feedback at the centers of dwarf galaxies, and now observationally we have a much more complete census of the satellite population of the Milky Way, thanks to DES and LSST coming up. But now I think, this is again a big picture motivation. You can turn the problem around and use our ability to model small scales and the connection between dark matter and observations, our ability to model that with higher fidelity, to just go out and set empirical bounds on these dark matter models, instead motivated from fundamental theory. So if I could briefly advertise some previous work I did, we used before the intergalactic gas to look for this canonical mass scale being all the dark matter. So typically you consider the limited case where one axion is all the dark matter. And that is very strongly ruled out by the Lyman alpha forest, and in fact by other probes, in particular the subhalo mass function of the Milky Way. But in this work, we wanted to return to a more fundamental motivation for axions, which typically comes from the so-called string axiverse. So there are lots of different ways in beyond standard model theories to produce axion-like particles. But in string theory, you have all these extra space-time dimensions that you compactify, and in the process of that compactification, you produce lots of different axions. So this is a plot pulled from this paper by Donny Marsh, where he calculates essentially the number of axions that you will produce in different space-time compactifications, and then you have the frequency of the time number of manifolds that give a certain number of axions, and you typically produce somewhere in the order of a few tens to 100 of these axion particles.
Sorry, can you unpack this plot for me a little bit? Like, so the H is on the axes is what? What is H100 and H of 200? And
these are Hodge numbers, and these relate directly to the manifolds that describe their compactification.
So some topological thing that defines something abstract. Okay.
Exactly, yeah.
And is the color scheme then the number of axions?
Color scheme is the number of manifolds that give certain Hodge numbers. So there's a huge, and it should be worth stressing that this is only a subset of all the manifolds that one could consider, because essentially it's a huge combinatorial calculation to do all these manifolds.
So the plot itself doesn't show the number of axions, it's just...
Not directly, but you can directly relate the Hodge numbers to the number of axions that you will produce. So it's just to say that if you produce axions, you may produce only a few, but you can also expect in other scenarios, your theory prior doesn't rule out the case that there are lots of these axion particles. And there is one more step, that then you have to promote these to be, abundant cosmologically. And again, I think it's fair to say there's a lot of theoretical uncertainty exactly how many of these axions would get promoted to be dark matter. But again, starting from the principle that you should prematurely rule out axions or any new physics just because it can't be all of the dark matter, this kind of motivates our approach to be agnostic and say, well, we'll have an axion of a certain mass, and it doesn't have to be all of the dark matter. It can contribute some subdominant contribution.
Is it totally fair to say that, at least from the phenomenological perspective, a parameter as a fraction of the critical density of 0.05 or 0.1 is, it's just what it is. But from a fundamental physics perspective, it's weirdly fine-tuned, right? To have it produced in the early universe so that today it is not 1,000,000 times the density or 10 to the minus 10 times the density, or that it somehow is because if it's a fraction of the cold dark matter, then something else is more. So then why are they similar? Is that something that's fair to sort of like flag up as something to be a little bit suspicious about? Or are there reasons why, if there's lots of different axions, they should all have roughly the same average energy densities?
I think that's a fair point. There's I think it's an unanswered question about how exactly to take these axions produced in the axiverse and, like you say, produce the exact right amount of energy density. That's not to say, so maybe I could show this slide, which is actually, is the final summary slide. So it's kind of showing all our observational constraints on axion energy mass on the x-axis and axion energy density on the y-axis. But I bring it up because the black region is a part of parameter space where this decay constant Fa, which is this early universe energy scale, is at the gut scale. And so again, that's this sort of coincidence. If you wanted some theoretical motivation to consider a particular part of axion parameter space that is well motivated, it's indicated by the black. So you can see what I was saying earlier, 10 to the minus 22 EV being all the dark matter about sits in this space around the gut scale.
I see. So this is saying, like, if, let's say you produce 10 different axions, one at 10 to the minus 30, one at 10 to the minus 29, one at 10 to the minus 28. So they each had different MAs, different masses, but all had the same FA, that you would be generating all of these fields in the universe with this y-axis of current average density. Is that how I should interpret the black dashed line?
You can take the axions one by one. So if you have an axion of a certain mass with a certain energy density, it'll have this FA.
And so would it make sense to say that they were all produced with kind of the same FA in some gut physics type, axiverse type fundamental physics model?
I'll be honest, I don't know the answer to that. But I don't think that that's necessarily true. And I think, more than that, one should consider mixed dark matter scenarios even beyond axions. It's entirely plausible that there is a very diverse dark sector that is equally as diverse as the standard model. And so we shouldn't rule out just the fact that there is all kinds of matter-like particles, dark photons, sterile neutrinos. These are all well motivated and could all contribute in some contribution to the total energy density. So that just more broadly motivates mixed dark sector models.
Yeah, although I guess you do have the problem that they all have to have similar energy densities. And
that's true. That is a fair point. Yeah. And so once you take axions as being, reasonably well motivated from fundamental theory, and you dig into their dynamical effect on cosmology, as we sort of said earlier, they can be dark matter candidates, but also dark energy candidates. And so, in fact, if you take any single axion with a potential like this, so typically you take this hat-shaped potential at some high energy scale Fa, it will acquire an angular degree of freedom, and then at some later time, that angular degree of freedom will break. So here, this is saying this is happening at the QCD temperature. So this is for axions specifically to resolve. So axions have a longer history as being invoked to resolve the strong CP problem in quantum chromodynamics. So in fact, if you relax that, this doesn't have to occur at the QCD phase transition. So just generically, you break that angular degree of freedom, the axion will start rolling down the potential. So that comes to the red line. And then it will start oscillating around the bottom of the potential. Essentially, you create two regimes cosmologically. Early on, it has an equation of state of -1, so it becomes dark energy-like. Later on, it oscillates around an equation of state of 0, and so it becomes, on time average, cold dark matter-like. And the time of that transition depends on the mass. And so in particular, as you get to the very lightest masses, this transition occurs after matter radiation equality, and so these lightest axions are behaving like dark energy for an important fraction of the cosmological history. And that means that these different masses will have different effects on different observables because of these different dynamics. And so, so coming back, focusing in on the paper, this has been looked at with CMB data pretty comprehensively. We in particular wanted to look at what large-scale structure has to say. And, as we keep alluding to, axions suppress power on small scales. So more specifically, these particles are very light, and so they have astrophysically large de Broglie wavelengths. And so at scales at and below that de Broglie wavelength, you will suppress the growth of structure because of the presence of these axions. And so here is a simulation cube of the large-scale structure. This is just the dark matter halo distribution. And it's flicking in and out of having just pure cold dark matter or having a 10% contribution of axions with mass 10 to the minus 25 electron volts. And hoping you can see that in the axion case, everything gets a bit dimmer. And that's essentially that you are suppressing the formation of low mass dark matter halos and small scale structure. And so this is the kind of signature that we're looking for in data. But of course, you can't see that directly. You have to trace the dark matter with visible objects. And so in this work, we use the galaxy surveys from the Sloan Digital Sky survey. So this is a cool movie that I took from the SDSS website where they show you a fly view of the SDSS survey. So each point is the position of a galaxy. The color coding is just different sub-surveys. And, hopefully when you can see the movie, it zooms in and you can see this cosmic wave structure. And so, you can look for the effect of axions in the galaxy distribution as a tracer. Finally, we want to just put empirical bounds on axions as being well-motivated particles, but also we wanted to consider the context of resolving tension in cosmology. And that's important, right? If we are going to use large-scale structure data in combination with CMB, we can only combine those data sets if there's not tension in their inference under a given model. And so under lambda CDM, there's a mildish tension between CMB measurements, which prefer a systematically higher value of this S8 parameter than various different large-scale structure experiments. So S8 is related to the variance of the clustering of matter when averaged over 8 megaparsec scales, and that's systematically higher by between 2 to 3 sigma when measured from CMB data.
You say mild and 2 to 3 sigma. I guess I'm more in the camp of it's persuasive enough to me that something's going on. It's not just random chance, because it's 2 to 3 sigma in a bunch of different independent data sets. So that even kind of takes away the look elsewhere effect. It wasn't some funky signal that was seen in one data set, because if you look at your own plot there, you've got KIDS, DES, HSC, redshift space distortions, galaxy clusters from SPT, TSZ, blah, 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 blah. Like, all of these are always 2 to 3 sigma small. So if one could do some combined tension thing, which would be very, very difficult, it would be very large.
Yeah, I mean, I agree. I'm just being conservative in my language, but I think that there is, there's something there that's worth investigating. Definitely. Yeah. This is often posed as an early versus late universe tension, and that's because S8 is defined at redshift 0, and so the CMB data is sort of indirectly measuring the clustering today. You have to assume some history of the universe to get from its measurement of early universe structure to today, whereas the large-scale structure experiments are probing it more directly. I guess one of the hypotheses of this work is that there's also a large versus small scales difference here as well, which is to say that the CMB data, including the lensing potential, is at the moment only modeled on relatively large scales. Whereas in particular the weak lensing, which is not a data set we consider here, are probing much, much smaller scales. And so that suggests that if you had a change in the cosmological model that stayed consistent with the large scale data but suppressed power on smaller scales, you may be able to simultaneously fit these two different measurements of the amplitude of clustering.
I guess you said you do include, and maybe you're going to answer this question in time, like some of the ground-based CMB stuff, which I guess is starting to measure to small enough CMB scales that maybe it is also the weak lensing scales. So that would be a way of testing that, I guess. But maybe you'll get to that.
We'll come to this. Yes, I think to preview is the lensing is most powerful, and that those data have not yet been released from the ground-based experiments on small enough scales.
Cool. Well, let's get into the details then. How have you used this data, and what does it tell us about these various masses of ultralight axions and whether or not they make up a significant fraction of the energy density of the universe?
Exactly. To start, I guess we should be more quantitative about what the effect of axions on the matter power spectrum is. So they cause a scale-dependent suppression in the clustering of matter. That's to say that at and below some characteristic genes wavelength, you will suppress the growth of structure, and that will depend on redshift Z, the energy density omega A, but in particular on the axion mass m, such that if you have lighter axions, the de Broglie wavelength gets larger, and so this gene's wavelength gets larger, and so the wave number of suppression gets smaller. And so at the bottom I'm showing linear matter power spectra, increasing axion mass from left to right. And in the bottom I'm showing the ratio to the cold dark matter limit, where I'm increasing the fraction of the dark matter that sits in axions from 0 up to 8%. And so you see that change in the scale dependence as you change the mass, and then as I increase the amount of axions, the strength of that suppression gets larger. So there's two not entirely degenerate effects from these two parameters that we vary. It's worth noting that a relatively small fraction of axions can cause quite a large suppression in the matter power spectrum, and that's similar to the effect of neutrinos, where you don't just reduce the amount of clustering in overdensities, but you also cause essentially a back reaction to the expansion as well. So you change the balance in the growth of structure. So you can get a sort of seemingly overstated effect from relatively small contributions. And so the grey area is indicative of the range of scales to which BOS data are sensitive. And so again, we hypothesized that axions could resolve the S8 tension by lowering the value of S8 inferred from large-scale experiments like CMB. And so this plot delves into that a little bit more. So at the top, we see the same as before. So it's the linear matter power spectrum. This is the total matter, so axions and cold dark matter, where I'm now going from the lambda CDM limit and then adding axions with different masses. Here I've set their energy densities to the 95% upper limit we get from our final constraint. So heavier axions have weaker constraints on the energy density, so the amount of axions gets stronger. And then I give the S8 values that you measure. And so at the bottom, I then show the ratio of these to the cold dark matter limit. You see always the axions suppress power. You see that, as before, lighter axions affect larger scales, but at heavier masses, more axions are allowed, and so the strength of that suppression is stronger. But in particular here, we're relating to the dashed line, which is the kernel, the filter in the integral that calculates sigma 8. So sigma 8 is a filtered version of the matter power spectrum, and that filter is the Fourier transform of a top hat filter in real space with radius 8 h over megaparsec. And so the dashed line is that filter in Fourier space, and you see that it integrates over the full power spectrum, but it's particularly sensitive to this range of scales between 0.1 and 1 h over megaparsec. And there's two key points here. The first is that if you increase the axion mass too much, so if you take the purple line at 10 to the minus 24 eV, its suppression is on scales too small to affect S8 appreciably. So that kind of sets an upper limit to the range of axion masses. But equally, if you go to too light axions, these will have strong constraints because they will heavily suppress large scales, which are well constrained by CMB. And so the amount of suppression they give on S8 is then small. And so there's really a sort of sweet spot around 10 to the minus 25 to 10 to the minus 27 EV, where axions can give much lower values of S8 than in the lambda CDM.
And is it fair to say, even though S8 is just like some arbitrary parameter, it's also kind of parameterizing kind of the distance scales where BOSS is most sensitive?
Exactly. So it's a good measure of what large scale structure experiments are sensitive to. I think I would contend that it's not such a good measure of what CMB experiments, including CMB lensing, is sensitive to. So the dotted line is the Kmax in the BOSS data that we use, which is at 0.4, whereas the dot dashed is approximately the smallest scale to which the Planck data set is sensitive, which we estimate from its sensitivity to axion cutoffs. These are the data that we look at. So we, of course, use Planck CMB data. So you've got TT, TE, EE power spectra, and the lensing potential power spectrum at the bottom. We also, for the first time, look at this with these ground-based experiments. So we take the latest data from ACT DR4 and from SPT 3G. These in particular add information at smaller scales, but they have not yet released lensing potential information, which should be, in the future, should be very constraining on these axion models. And so what this plot's hopefully trying to convey is that if you go to, as you were saying before, we saw it within the matter power spectrum, that if you go to these lighter axions, their effects on the CMB are strong enough, and here this is exaggerated for a very large axion energy density, but that you can already rule out these very light axions with CMB data, and in fact already with Planck data. In particular, if you take these lighter axions, what they do is they change the ratio of matter to radiation in the early universe, and so they change the relative peaks, the peak sizes in the CMB, so that's where a lot of the constraining power comes from. And also in the lensing potential, you have this is a sort of more close tracer of the matter power spectrum itself, and so you see this scale-dependent suppression arising from axions. If you go to the dark energy-like axions, they actually they're mostly constrained through the ISW effect. So because they contribute to dark energy at late times, they basically change the amount of ISW that you expect, and so it's the very largest scales in the CMB that is constraining on these very, very light dark energy-like axions. But if you take 10 to the minus 25 EV, that's dashed line, you can't see the dashed line. And so, CMB data is even these ACT and SPT data are losing sensitivity at the moment to heavier axions. Okay, so just to sort of flag up really that over previous work, we've updated the Planck data that we use. So we moved from 2015 up to 2018 Planck data. And in fact, for the lightest axions, so atom below 10 to the minus 28 eV, we get an improvement in the axion constraint. And that's really being driven by the updated polarization measurements in the 2018 analysis. So in this plot, I'm showing now contours. These are marginalized posteriors on cosmological parameters, axion energy density on the far right, and then tau and AS on the left. And here I'm systematically switching parts of the 2015 Planck data to the 2018 data set. And hopefully you can see that when you go from the red to the yellow, that's when I put in the new low L likelihood, i.e. which contains this reionization bump information. And this stronger and lower value of tau breaks this degeneracy with AS and with axions in the favor of strengthening the constraint.
So for people who might be first encountering these parameters, AS is the amplitude of the primordial curvature perturbations or density perturbations, and then tau is the optical depth. So it's measuring how far the photons can travel. A bigger value is that they travel further or get stopped sooner.
They travel further, right? They have a larger optical depth.
Yeah, and then a smaller value means that they don't travel so far in the current universe before being reionized.
And so these are, in fact, Planck data is sensitive to this degenerate combination, so AS e to the minus 2 tau, which is the amplitude affected by the reionization damping of the power spectra. But they're both degenerate with axions, because these very lightest axions, so here I'm showing specifically 10 to the minus 30 eV, are affected by large scales, and so they open up this degeneracy with the primordial spectrum. And so to really drive home the point that there are two different regimes of axions and they have different constraints and they do different things for tensions, this plot is, again, these marginalized posteriors. Again, I'm showing axion energy density on the far right. Now I'm showing the Hubble parameter H, the total matter energy density omega m, and this S8 amplitude today parameter. And then I'm showing different axion masses, so lambda CDM, adding axions and decreasing the mass. And you see that when it's dark energy like these very lightest axions, you have a degeneracy with H to lower values. And that's because they're acting like dark energy, so they're changing the age of the universe, but we measure the angular scale of the perturbations so well that to compensate, you have to lower H to make everything fit together without inducing a phase shift to the CMB. And so actually, if you take these lightest axions, they tend to lower H, and so that goes in the wrong direction for resolving the Hubble tension. They also increase omega m a bit, and that's because they now become degenerate with the dark energy density. And so you still have the same amount of cold dark matter, you're just adding more axions, which today do count to the matter because we define omega m today. But for these lighter axions, you see this very strong degeneracy of S8, and these are also more poorly constrained, so you can have more axions and get to lower S8 at these higher masses. And so the next section in the paper is considering these ground-based CMB experiments, so data from ACT-DR4, SPT3G. We also consider a compendium with all three CMB data sets and add galaxy BAO and supernova data, so for a sort of full large-scale cosmological combination. We only consider the case of 10 to the minus 25 eV. We defer a more thorough study of these data, in particular for upcoming lensing data sets, which should be released soon. And what we find is that actually you slightly weaken the constraint on axions. So in particular, just the bottom right panel here, this is the marginalized constraint on the axion energy density. In particular, when you add ACT data, you shift the posterior weight slightly to larger axion energy densities. And this is actually consistent with what you see with neutrinos as well. And it's being driven by the amount of lensing that you get in ACT and SPT. So Planck is known for having this A lens anomaly, so this 2 sigma-ish anomaly where they have slightly more lensing in affecting the CMB primary anisotropies than you expect given baseline cosmological model. And because they want more lensing, that means that they don't like things that suppress structure like neutrinos or axions. Whereas ACT and SPT, they have a consistent value of this A lens parameter, and so they like less lensing than Planck does, and so they're happier with things that suppress structure like neutrinos and axions. And so similarly with neutrinos, you actually see a weakening in the neutrino constraint when you add ACT to Planck data, and you see the same thing with axions in our analysis.
I think I have a basic statistics misconception here, so I'm not sure. I think I might need to just go away and think about this and read up. It seems weird that adding data would widen the constraint rather than just moving it up and narrowing it. If someone had given me a multi-choice question earlier about whether that was even possible, I might have said no. So I'm going to have to work out why I'm confused about that.
Yeah, and I think the thing to bear in mind is we're looking at the marginalized posterior here, but this has been integrated over a bunch of other parameters. And so in a Bayesian sense, you can have the posterior that is sitting in one place. You can add some data, and that data may like you to shift that posterior slightly. And so once you marginalize over all those other parameters, that can lead to a weakening of a constraint on a certain parameter. But it doesn't necessarily mean, A, that the entire posterior weight hasn't shrunk, that the data hasn't given you more information on your model. This is just, this could be essentially a marginalization effect.
So it's essentially the n-dimensional posterior has moved somewhere in that higher dimension where it is wider on this particular parameter. I see. Okay, that makes sense.
And so to come back to the S8 hypothesis, if you take that full compendium of data, analyze it under lambda CDM, and then analyze it under axions, here with that mass of 10 to the minus 25 EV, and compare it to fiducial lambda CDM analyses from the weak lensing experiments. So these are the 3x2 analyses from Des and Kids. So that's a combination of galaxy clustering and cosmic shear. Again, so just to say, axion energy density on the right, matter energy density, omega m, and the S8 parameter on the left. You see the S8 tension. So in this panel, blue is the constraint in the S8 omega m plane from CMB BAO and the supernova under lambda CDM. And the green and the yellow is the constraint from Des and Kids. And you see that the larger scale data prefer this higher value of S8. But when I allow for axions, because of this very strong degeneracy between axions and S8, to increase the amount of axions, I naturally get these lower values of S8. You can sort of naturally recover these lower values of S8 that are consistent with Des and Kids. Now, to be clear, this does not yet say whether the tension has been resolved. One then needs to analyze these 3x2 data under this extended model to see whether really under that new model, the data sets are now more consistent than they were under lambda CDM. And so this paper is essentially answering the first half of that question, which is what do galaxy clustering data, specifically from BOSS, have to say about this?
I mean, that's an important caveat, but the changing of the model will have a much bigger effect on the CMB stuff because you are having to use the model to propagate the stuff measured in the CMB to today, whereas the Des and Kids is a much more direct measurement, so should be less model dependent. So
that's potentially true. So actually, as a partial aside, typically in the literature, when people look at using weak lensing data, they will take the S8 constraint from a weak lensing experiment and use that as a proxy for all the information contained in that data set. So we could in principle do that ourselves here, but I would urge a strong word of caution about that because it is a very good measure of the information content under lambda CDM, but you need to explicitly check whether that remains the case under any given extended model. And in particular, precisely because we know that these sorts of models like axions are changing the nonlinear dynamics at the scales that these weak lensing experiments are sensitive to, that all the information may no longer be contained in that S8 prior. Okay, so we want to use galaxy clustering information, but in which case we need to go beyond the simple linear order calculations that we all do in a modified Einstein-Boltzmann code like axion CAM. And so to do that, we use the so-called effective field theory of large-scale structure. So this has a huge literature behind it, and this is just a very schematic view of how the model works. So now we're going to be modeling the galaxy power spectrum as a function of wave number k, but also we're now going to become sensitive to redshift space effects. So the power spectrum is going to be in general anisotropic, and so now we do a multipole expansion of this anisotropic power spectrum. So L indexes the multipoles. So in particular, we look at the even numbered multipoles, which are non-zero, so the monopole, the quadrupole, and the hexadecapole. And this has various terms that go into it. You have a set of terms that capture the linear order physics with a Kaiser-like model for linear bias and linear redshift space distortions. We then have a bunch of terms that capture perturbative corrections to the matter power spectrum up to one loop in order. We then also have a bunch of terms that are called counter terms or ultraviolet counter terms that capture the coupling of smaller scale physics back to the larger scales. So these captures in particular a lot of the non-linearities. And then we also have a bunch of terms that capture stochasticity in the data themselves. And we also do infrared resummation, so that's the effect of long wavelength displacements on the matter power spectrum, and we account for the Alcock opportunity distortion as well. But the key point in all of this framework is that these terms have a bunch of free parameters, but they only depend on axions through the linear matter power spectrum. And so by calculating the effect of axions through the linear matter power spectrum and remarginalizing all the nuisance parameters that account for the strength of these different effects, we can capture the effect of axions up to mildly nonlinear regimes. So we take this to around a scale of 0.4 h over megaparsec. And so this is the effect. So these are the galaxy power spectrum multipoles, monopole at the top, quadrupole at the bottom. Again, we're increasing axion mass from left to right and the amount of axions from 0 up to 8%. For these lightest axions, essentially, so these are modeled for the BOSS data, and so the scale of the suppression is on scales larger than to which the BOSS data are sensitive, and so the whole power spectrum just gets suppressed. But for the 10 to the minus 26 EV axion, you start to see this scale-dependent suppression, which gets stronger as you add more axions. But in fact, for the quadrupole, we see an interesting effect, which is that where we add more axions, we actually get a small boost in the galaxy quadrupole. And this arises because these scales are affected by the fingers of God effect. So that's the fact that in redshift space, overdense structures appear elongated due to peculiar velocities relative to the Hubble flow. And so that suppresses power at those scales. But when you add some axions, you weaken the strength of those overdensities. The peculiar velocities of infill are weaker, and so the amount of that redshift space distortion is reduced. And so you get a relative enhancement in the quadrupole relative to the cold dark matter limit. And you actually see this in all the higher order terms of the multipole expansion. So then this confronts it with the data that we use. The points of error bars are measurements from the BOSS data set. In blue is the monopole, red is the quadrupole, yellow is the hexadecapole. The green is a reconstruction of the real space power spectrum. So we project away redshift space effects for these smaller scales because in that regime, these nonlinear redshift space distortions are harder to model. And so rather than attempting to model them, we conservatively sort of project them away and just reconstruct the real space clustering of the galaxies at smaller scales. That's the statistic Q0. I've overlaid some maximum posterior models. In solid and in dashed are the maximum posterior values from our fiducial BOSS and BOSS plus Planck analyses. And then in dotted, I just boost up the amount of axions at the expense of cold dark matter, and you see this very strong scale-dependent suppression, as you can start to get a sense that having access to the smaller scale information is going to increase our sensitivity to these heavier axions. We also looked at the bispectrum in this work, which will be in the paper, but essentially this is only at the moment modeled in relatively large scales, and so the effect of axions is marginal in the bispectrum at the moment.
What is the limiting factor for small scales in the bispectrum?
So it's just the number of order in the effective field theory perturbative expansion hasn't yet been calculated. I think that is that's a very active field. So I think in the next few months, they do hope to improve their modeling of that. And then we would hope to work out how axions fit into that as well. The big story picture here is that we get stronger constraints on axions from the traditional BOSS data. And what is more, that in general, axions improve the amount of consistency between Planck and BOSS. So if we take as an example this 10 to the minus 25 EV, these are the posterior contours for BOSS alone in blue, Planck alone in yellow, and the combined constraint in black. Axion energy density on the left, you see that the BOSS data now gives you some stronger constraint on these axions, and the strongest constraint comes from the combined analysis. And in so doing, you essentially increase the amount of overlap in these posterior volumes, which is perhaps not surprising as we've added an extra parameter, but the degeneracy directions with that parameter increases the amount of overlap. So if you go to the SA to make an M plane, the yellow and the blue have much more overlap than in the lambda CDM limit, where in the yellow one you don't get to these lower values of S8 without axions. When you take the combined constraint, Planck has much stronger constraints on cosmological parameters, so it effectively fixes all the cosmological parameters. And so it says that you must have slightly higher values of S8, although you still go to lower values than in the lambda CDM limits. And to maintain a good fit to the BOSS data, it prefers a lower value of the linear galaxy bias B1. So that's the parameter on the far right. So without Planck data, you have quite a broad constraint on the galaxy bias. When you add Planck data, just because it says you have to have these, in particular, higher amplitude cosmological parameters, you move along the degeneracy direction between B1 and S8 towards lower values of B1, but still with sort of physically plausible values of the galaxy bias. So as you alluded to earlier, there's this sort of anomalous region. So at all masses, the story is quite consistent, but at a particular mass of 10 to the minus 26 EV, you actually see that BOSS has a mild preference for axions of that mass in some small contributions. This is about 10% of the dark matter. So that's omega AH squared on the far left. But in particular, this is quite strongly ruled out by Planck by itself. So if you take the amount of axions that BOSS likes and put it into the Planck data, you would have very strong tension. And so in particular, under this, at this particular mass, you increase the amount of tension between the two data sets. And so the robustness of combining the two data sets at this mass is reduced as a consequence. It's worth commenting, I think, two things. The first is that, maybe three things. The first is that this is fairly robust to prior choices. And particularly I should say actually that all the time we look at BOSS data, we do not use a BBM prior on the baryon density. Typically that is done in BOSS analyses. But even if you add a BBM prior, this sort of preference for axions doesn't go away. But it is very degenerate with NS. And so if you had some sort of theory prior that your NS value should be closer to 1, only mildly different from scalar variance, then this preference for axions would go away. But it's worth saying that you do actually improve the fit to BOSS data. So you have an improvement in the chi-squared by about 8 at the maximum likelihood point when you add axions of this mass.
Do you have any kind of physical thoughts about this? Actually, before you answer the physics question, there must be funky things happening in the n-dimensional space again here, because if this was all the data, then combining the blue and the yellow should not give these blacks, right? Because yes, the yellow is more constraining, but the black is like lying on top of the yellow instead of kind of halfway in between. So there must be some reason in the higher dimensional space why the yellow just won't let it move away. And maybe this plays a part with the kind of physics interpretation.
Planck is just so much more constraining on all the other cosmological parameters at the moment that it essentially fixes all the cosmological parameters to its values. And then it just says to the boss data, do the best you can with the other parameters that you have. And so you see that when you combine it, the axion constraint is slightly weaker. It's being dragged to slightly higher values of axion. But Planck just says you can't have that much axions, because then you have to have a very low value of ns, in particular an even lower value of the amplitude. And so Planck wins over in that tussle. But I would stress the point that essentially I'm arguing that this joint constraint is less robust under axions than it is under lambda CDM, because I have exacerbated any tension that exists between the data sets with this particular mass. It actually stresses the importance. So in the paper we show, tension values for S8, because that's what we typically do in the community, but really we need to consider the tension in the full parameter space. So we also use this parameter difference posterior distribution in the paper to calculate, essentially how many sigma away are these posteriors when considering all the parameters, not just the marginalized constraints. And I think in follow-up work, we'd like to also look at this with other more Bayesian approaches to assessing tension, like the suspiciousness or the posterior predictive distribution. We shouldn't place undue weight on tension in marginalized parameters when in fact we're constraining these multi-dimensional posterior distributions.
So just what do you think is potentially physically happening here? Like, is there something to keep one's eye on, or is this a bit of a look elsewhere effect sort of thing? You look curiously at enough different things, eventually something interesting looks like it's happened, but it hasn't happened.
There is definitely some look elsewhere effect here, right? Because the way that we scan the axion mass is that we don't smoothly vary the axion mass, but rather we consider lots of different fixed axion masses. That's actually for technical reasons. If you try to sample the axion mass as well, you do have a very difficult degeneracy. You have a sort of U-shaped degeneracy that is quite hard to sample. So we account for that by sampling at fixed axion masses. So we essentially are considering 10 or 12 different models. And so perhaps it's not surprising that in one of those 12 models we find this discrepancy. One possibility comes back to this A-lens issue. So that because Planck likes 2 sigma-ish more lensing than the fiducial model, if that was actually a systematic in the Planck data, you would be artificially ruling out an amount of axions that may bring these into more consistency. But it would not address the fact that you have to have low values of NS to have these higher axion energy densities. So this is the summary on the constraints. So these are the 95% upper limits on the axion energy density as a function of axion mass. In blue is the constraint from Planck, and in red is the combined constraint with Boss. So as I was saying earlier, you see the typical U-shaped constraint, where as you get to heavier axions, the small scale suppression is on scales too small to probe with the data, and so the constraint gets weaker. In the other direction, these are dark energy-like axions, and in fact they only start oscillating at later and later times until you eventually become indistinguishable from just a cosmological constant. So the axion hasn't started oscillating yet. And so you lose sensitivity in that direction as well. And then with Boss, you strengthen the constraint across all the masses. In particular, you gain, because of smaller scale information, you gain sensitivity to slightly heavier axions. But Boss still loses sensitivity at this 10 to the minus 24 EV. And you see the one case, this 10 to the minus 26 EV axion, where adding Boss weakens the constraint. But that's being driven by this tension between the two data sets. And so this is what it does for S8. So this is the same plot as before, the joint Planck plus Bose constraints. But now I've color-coded the samples by the value of S8 that you get. And so you can see that in this sort of sweet spot of dark matter-like axions that are not too heavy, so the suppression happens from too small scales to affect S8. At the upper end of the axion energy density, you get these lower values of S8 from having axions. And so if you return to that plot I showed earlier, but now update it with Planck plus Bose, here at 10 to the minus 25 eV, you have a stronger constraint on the amount of axions you can have. So you can't get to such low S8 values, but you can get to slightly lower S8 values than the Malanda CDM limit. And so although there's not such overlap, there's still a tail out to lower values of S8. But again, I do stress, to interpret this plot with some caution, because not only are we not looking at the weak lensing data under the extended model, so it's not really fair to assess tension. Also, this KIDS 3x2 contains galaxy clustering information from Bose, so there's not even entire independence between these data sets. But I think it's indicative nonetheless that it's sort of interesting to consider axions as still being able to lower S8 with CMB and galaxy clustering. Last plot I want to show, which I think I showed at the beginning as well, is the kind of state of play of axions. So this is a compendium of cosmological constraints on ultralight axions. Anything in solid is what is ruled out at 95% confidence. Axion mass on the x-axis, energy density on the y-axis. You see the CMB and Bose galaxy clustering constraints at the lower masses. You have the Lyman alpha forest constraints at even heavier axions, because they're essentially probing very small scales in the IGM that we can model to quasi-linear scales to much smaller scales using those data. But in particular, these solid lines are projections for different experiments. So the blue line is a projection from the CMB S4 experiment, particular lensing information in S4, and you will gain sensitivity to heavy axions and kind of attack this window of unexplored axions, which haven't been looked at with empirical data yet, but could be where the sort of parameter space to resolve things like the S8 tension.
So one of the reasons that this kind of 10 to the minus 22, 10 to the minus 21 was interesting is that the de Broglie wavelength was kind of 10% of the size of a galaxy or something. So presumably going to lower masses, it's getting even bigger. Therefore, some galaxies below a certain mass shouldn't even form if it's 100% of the dark matter. Is that what this kind of DES REI constraint is coming from? And I should read from this plot that if it's 0.3 of the dark matter, that's actually not ruled out.
Yeah, so first to be clear, I've switched omega here. So this is fraction of the total energy density, just to clarify. And so in fact, the DES was actually analysis of cosmic shear data. This came out of our group. It was led by Mona Dentler at Göttingen. And she looked at cosmic shear data in DES year 1, but under the limited case where axions could be all the dark matter. And essentially the non-detection of a small-scale suppression in cosmic shear power spectra set an upper limit at about 10 to the minus 23 eV. And the reionization constraint actually comes from observations of the early universe galaxy luminosity functions, so these UV luminosity functions. Essentially the detection of galaxies of a certain mass in the early universe, again, rules out suppressions in structure. I think more broadly, you're right that if you had an axion that was too light being all the dark matter, you essentially wouldn't form even Milky Way-like halos. And so just the fact that we exist kind of rules out this parameter space. But it's not clear, you could still have an axion quite light being, an appreciable fraction of the dark matter. You would still have cold dark matter to form galaxies, and it hasn't been observationally constrained yet.
Right, like about 0.25 of the dark matter density or something. I see. Okay, interesting. Mm-hmm. Whereas, once you get to the very small masses, the CMB is rolling you out down to 10 to the minus 2. There is this window. That's interesting. Okay. And so what, maybe, again, this is a thing, if I go away and think about it, it'll be fine. But why does Lyman alpha have this very sharp vertical, why doesn't it extend to the lower masses too?
This comes from, I think, an analysis of the BOSS Lyman alpha forest data. And essentially, the particular data set this comes from is not modeled for larger scales than this. And so you don't empirically put a constraint on lighter axions that affect larger scales. But I do think that you probably could use some of the Lyman alpha forest data to attack this window. I suspect that we have the data. In fact, if you looked at the DES data, the limitation is rather, we have the data, the limitation is the modeling, I think, that you become sensitive to nonlinearities that are harder to model in this regime.
Cool. All right. So yeah, where to next? I guess we've just hinted at one of the things. We extend the modeling of the Lyman alpha forest and DES data to these smaller scales with these different dark matter models and see what happens. But and you've also mentioned a few times the lensing on small scales from things like ACT and SPT would be super useful. But what else should we expect in the near future?
Yeah. So yeah, I think observationally, the data is going to come. We have, small scale CMB, lensing to come. We have all these large scale structure surveys. They're going to be very powerful. I think that it's on the modeling side where we still have work to do. So we've been using this effective field theory approach that is good up to these sort of mildly nonlinear scales. It probably is not, at the moment at least, good enough to get to very small scales. So, cosmic shear is sensitive to up to around K of 1 h/over megaparsec, conservatively. And so there you're in the fully nonlinear regime. And so, the effect, nonlinear axion dynamics may become more important. Things like the quantum pressure, which we only model at the moment through its sort of changing the initial conditions. We may need to start to think about how that's interacting with cosmological structure formation. So I think that's where I think that a lot of the work should go, is into some of this nonlinear modeling. We have, for this DES analysis, we have a halo model that we have been building along those lines. And then also, I think, just to come back to S8, we talk about assessing tension, consistency between CMB and large-scale structure data through their values of S8. But probably we need to move beyond that, right, and consider where in scale and redshift are data actually constraining the amounts of structure in the universe, and where they are consistent or not consistent. Rather than trying to extrapolate everything to a particular number, we really need to be looking at P of K as a function of Z as constrained from all these different data sets.
I guess when with each individual data set the tension's only 2 to 3 sigma, it's hard to do what you just described, because you're kind of smearing out the deviation and everything will look more consistent. What would be really cool is if one could do a kind of combined DES, KIDS, BOSS, galaxy clusters analysis to get it to sort of 5-6 sigma, and then you could kind of see where the deviations are happening. But I guess these data sets and analysis methods the data sets are kind of overlapping, and the analysis methods are so different that a combined analysis is certainly not trivial.
Yeah, I mean, it's worth also bringing up systematics, right? That we need to be, as with the Hubble tension, we need to be as absolutely confident that there's not unmodeled systematics that are driving. I have heard word of, for example, a joint analysis between DES and KIDS. I believe that's underway, and that will help to address, whether there is common systematics or not. So, but absolutely, I think combined analyses under extended models are the future.
Yeah, what work being done in cosmology at the moment do you think is particularly underappreciated by the community?
So I'm not sure if it's really underappreciated. For example, you had a thing about this, about parity violating signals. So I think that, for example, birefringence is quite interesting, and it connects to axions because there's kind of another dimension to this plot, which I've ignored, which is it's sort of coupling to axions can also have couplings to standard model things like photons, for example, through like a Chern-Simons interaction. And so birefringence is sensitive to axions and its coupling to photons. And, there's been possible hints of birefringence, difficult to disentangle, galactic contamination. But I think that I think it seems like it's going to be an important part of what comes out of these next 10 years of CMB experiments will be measurements of birefringence with high resolution. And we may start to look for sort of spectral features in birefringence, which you could associate with features in an axion model, for example.
Yeah, that's very exciting. Maybe it's underappreciated by the cosmology community, but it doesn't seem to be underappreciated by the viewers of this channel. Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos. And click like to help with YouTube algorithms. Both you and the channel will benefit, as YouTube will know to recommend more stuff like this to you. And share the channel with your colleagues. If you have any questions or suggestions, leave a comment. And thanks, Keir, for the great talk.
Thank you, Sean.
Well, I hope you enjoyed that talk. That was actually recorded in December, so in some ways I'm talking from the future now, although I guess it's the past to anyone watching the video. All of the cosmology talks now, or at least most of them, have follow-up live discussions, which we're calling mini workshops. Keir's talk is no exception. It will be grouped with Richard's talk from last year, and the live discussion mini workshop will be happening on the 1st of February at 6 p.m. UTC time. All cosmologists are welcome to attend. There will be a bunch of invited adjacent experts attending, as well as Keir's co-authors and Richard's co-authors. So if you have any questions about this talk, here's the chance to ask Keir and Richard and his co-authors, and to see what other experts say, so you're not just getting their one-sided opinion. And it's also a chance to see what the experts say when they're talking to each other on this particular topic. If you want to attend, there is a mail list sign-up form in the description to this video, and if you join that mailing list, we'll send you an email with the Zoom room and passcode for you to attend. Again, all cosmologists are welcome to come. Hopefully see you there. And yeah, other talks later on will also have associated mini workshops. So if you sign up to the mailing list, you'll be able to find out about them as well.